So here's what that relationship looks like graphically for silicon dioxide. If you plot this resist to deposit ratio versus undercut, what you can see is that the blue dot points represent unstable structures or significantly bowing structures, structures that were effectively deflected, perhaps borderline, are depicted with the black squares, and structures that were both structurally sound and had excellent liftoff were all depicted in the green triangles. Now, obviously, there are other factors that come into play in determining an optimal design. There's known collimation effects that occur with a thicker top resist layer, but our findings were that there was somewhat of an asymptotic relationship with that around 3 microns thickness for the top layer resist, where the benefit of going thicker didn't really have as significant a benefit as going, say, from 2 to 3 microns in thickness. So, in summary, these relationships yielded this predictive window for kind of setting up a process in context of what the bilayer structure needed to look like relative to the deposit thickness to get good outcomes. Next, we basically looked at aluminum oxide, and essentially we found very much the same results as we did with the silicon dioxide, but they seem to be offset by a factor. And it's believed that offset is related to the deposition properties of the particular material. We did also find that the thicker top resist here, more collimation of effect, seemed to basically be beneficial, more so than with the case of the silicon dioxide. That's likely related to the throw or momentum properties of the molecules under deposition.